Boys and girls, welcome back. I am so excited to see you all and to move on to the physical science portion of Intro to Chemistry and Physics, or as it's on your schedule, physical science. Same thing. Um, so I hope you all had a great Christmas break. We are done with the chemistry stuff. We are moving on to physical science world of forces in motion. And by the way, if you've ever talked to anybody that's taking AP Physics 1 right now, this is not AP Physics 1 level work. AP Physics 1 is all about forces in motion. It is the absolute hardest AP test there is. It has the lowest passing rate because it is the most difficult AP class there is. But we are not going to get anywhere near that level of difficulty since this is a general ed class. So if you've talked to some of my kids that have cried on some of their assignments in AP Physics 1, we are not going to be doing anything like that. So no worries. Don't be freaking out. I had some people about ready to spaz before Christmas was starting because they thought we were going to do that level of work. We are not. Okay, this is a lot easier. Anyways, as you can probably see on my background here, we have some jets. And as you might have guessed, these are jets that are breaking the sound barrier. I was not alive whenever the sound barrier was broke in the very first time ever. I think it was in '76. Chuck Yeager, he was the one that broke the sound barrier, and it is a literal barrier that you have to literally break. There's a big sonic boom that's given off, and there's this cloud around your airplane that of compressed air that you literally have to punch through to be able to go faster than the speed of sound. Uh, I was alive though whenever the sound barrier was broken by a vehicle. This was in October 15th, 1997. I remember watching this on TV. This was Andy Green who broke the sound barrier on the ground in a jet powered car. Now, the first actual car to break the sound barrier was also in the 70s. It was a missile fueled car. Someone just strapped a missile to a car, and but that was not recorded by Guinness. So Andy Green in '97 was the first one to officially break the sound barrier. You have to do it two runs. He did it both times. There was actually two cars competing, and one of the cars did not succeed. It like turned over and slid for like 2 miles on its side. Nobody was injured, but I remember watching on TV when they broke the sound barrier. It was pretty cool. They were out in the big salt flats. Anyways, you might be thinking, okay, how fast is the speed of sound? Short answer is it's very fast. I remember they interviewed this guy that broke the sound barrier. He said he would sit in his car and he's driving his car. He can't really steer it very much, and they had mile markers set up. And he said, you could see the mile markers going 1, 2, 3 every second. A mile was going by. That's crazy fast. Anyways, to be able to get to that speed. So, how would we, if we had to measure what the speed of sound was, how would we do that? And it's actually really easy to do. Um, this is a video I've stolen off the internet. Typically, I would take you down to the football field and show you this. But these are kids out on a football field. I'm going to get this turned up. I don't know if you can hear it. There's a metronome, and all they are told to do, the metronome is by Emma in the very front, and they are just told to clap their hands. When you hear the metronome, get in the beat, boom, 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 and clap your hands at the same beat. Now, each of these kids are spread out 10 meters apart. So that means our gray sweatshirt dude in the very back is like 240 feet away. He's 80 meters away, almost a football field length. Um, and he is the farthest one. But watch their hands as they switch over to slow motion. I mean, to me, it looks like they're clapping. It looks like they're clapping in sync, but they're actually are not. Watch their hands. There's actually a pulse. So you might be asking yourself, why is it that Emma in the front claps her hands first, and then everybody claps their hands in that order? Boom, 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 boom. So this is video footage that has been slowed down 16 times. And although it may look to us like they are clapping perfectly in sync, this metronome that's up by Emma, the sound wave has to travel at a specific sound. It is very fast, but it is not instantaneous. So if I wanted to find out how fast speed travels, I need to be able to have some tools in my toolbox to be able to do that. Because the sound wave hitting Emma at the first, she's the first one to hear it, so she's being able to keep track of the metronome pretty well. But our dude in the very back, gray sweatshirt dude, since the sound takes longer to get to him, he hears it after everybody else does. So when he claps his hands, he's actually clapping last because it's taken long enough for the sound wave to travel from Emma to the front to gray sweatshirt in the back. And everybody else in between kind of falls in line. So what we are working up to our speed equation, which it's how far a distance something travels in a certain amount of time. So if I cracked out my stopwatch here, I could say Emma's in the front, gray sweatshirt's in the back. If I know that distance, 80 meters, and I could calculate how long it takes to get there, I could say distance divided by time gives me our speed. But before we do, we need to talk a little bit about some terminology. Okay, we need to talk about some terms and what those things mean. So let's go over to PHET. First thing, and this is all we're talking about today because this is kind of a longer video, is what is the difference between these two terms, distance and displacement? Okay, so that's all we're going to talk about today. So, distance is literally how many steps that we take. Like if I'm going to walk from Emma in the front to gray sweatshirt in the back, I'm going to have to travel a total distance of 80 meters. Okay, now sometimes your distance and your displacement are the same thing. For instance, distance is the total number of steps you take. So I was really excited when we bought a house on Liberty Road because it was so close to work. It was like 5 miles. Okay. So if I wanted to travel from home to work, if I just drove straight there, it was 5 miles. Okay, that's literally how many miles I put on my car if I drove in a straight line. So my distance is literally how many miles were on your speedometer. Your displacement is a measure in a straight line from where you start to where you end it. So if I could drive in a straight line, it would be 5 miles. Awesome. Okay, now here's the problem. We had our kid, and I had to take my kid to the babysitter right after we moved in there. We pretty much had a kid. So all the way over here is Duck Creek, where my babysitter was. Okay, you see the problem that's going on here? Um, I got a call from Jamaica. So if I started driving from my house and I went up here and went on 519 and then turned off and then went up past Dittany and came out here at Duck Creek, and then I drove all the way back on that same route, and then I came back here and went to work. If I were to measure from where I started to work, my displacement is still 5 miles. Okay, this was where I started. This is where I ended. I'm only 5 miles away from where I started. But by the time I drive all the way to Duck Creek, drop my kid off, and then come back to work, I've really drove 40 miles. Okay, so here is the difference in between my two words. So distance is path dependent. Okay, this is literally how many steps I take. Displacement, whoops, helps if I spelled it right. Displacement does not. Displacement is start to finish. Okay. This is a straight line. So it really doesn't matter how far I go to get from my starting line to my finishing line, which is work. No matter which path I go, whether here or drive out this way, my displacement is always going to be 5 miles if I always start here and I always finish there. But my distance will be longer if I go a different route. So the way that this is shown is if I'm in here and I drive, let's say this is where my house is, and I'm going to drive past work and then I'm going to have to make a U-turn and come back. So I've actually drove past the house, and then once I drive past the house, I got to turn around and come back. If I show the values here, I've drove 30 miles and then I came back and drove another 20 miles. I've drove 50 miles total. But the sum the sum of my total displacement is only 10 miles still. Okay. This works in two dimensions too. So if I'm driving around and let's say that let's say my work is here. This is my house. I'm going to start from my house and here is my work. Let's say I moved and I'm farther away from work now. And I can't drive in a straight line. If I drive up this way and I come up here and then I drive and I got to turn off on this road onto another road and then I drive here and then I got to turn off on another road and from here to here I have to drive there again. So I've turned off on three different roads. I've drove 21 miles plus 14 miles plus 15 miles. So I've driven about 45 miles to be able to get to my house. But my displacement, well, my displacement is just 30 miles. Okay. This is my distance, the total path that I had to take to get there. But this is my displacement. My displacement is 30 miles. It is a direct line. Okay, let's do some example problems of this. Let's clear this off. So let's clear this off too. Let's do a couple example problems. So I'm going to start from here at my origin. Let's say I drive and I'm just going to go east and we'll do meters instead of miles for this. I'm going to drive 20 miles and or 20 meters, and then I'm going to turn around and I'm going to drive back 10 meters. Okay, so based on this, I'm going to go east 20 meters and then I'm going to walk back west 10 meters. What is my total distance that I've traveled? Okay, so enough time there. I've walked 20 meters and then I've also walked 10 more meters coming back. My total distance traveled is going to be 30 meters. Now, what do you think my total displacement is going to be? Now, be careful on this. Okay, so my total displacement is a measure of where I've started and where I've ended. Now, I've been lying to you up until now. Displacement is a vector. Vectors tell you two pieces of information. They tell you a magnitude and a direction. Magnitude just means what's your distance or how much, and your direction tells you in what way. So if I click on this sum, the sum of all of these vectors tells me my displacement, which is this value, is going to be 10 meters. But I need to be specific and say it should be 10 meters to the east that way. Because what if I did not drive directly east? What if I drove this way and then I drove back down this way? Haha. That means I've actually drove now a total distance of 15.5 meters in that direction. So again, it's always a measure of where you started and where you ended. Okay, distance, displacements. Okay, nifty stuff. All right, let's see. Let's do one or two more. Go away. Let me just clear all this up. Oh, okay. All right, let's do one more. Yeah, let's do a couple more. I'm late for a meeting. I'm gonna have to pause this. All right, so our next example, let's say we have the situation like you see here. We're going out our front door. We're going to go 7.1 meters to the northeast, and then we're going to go 7.1 meters to the northwest. So first thing, what is my total distance traveled, the total number of steps that I've taken? All right. So if I'm going to look at the total distance traveled, it's going to be the total number of steps I've taken. So I've taken 7.1 meters steps this way and 7.1 meters steps that way. So that I add those together and I get 14.2 meters that I've actually covered distance wise, like the odometer in my car. So based on what you're seeing on this chart here, what would be the total displacement? That is the measure from where I started to where I ended. Now be careful on this. All right. So if you just said 10 meters, you would actually be wrong because a displacement is a vector. It tells you two pieces of information, a distance and a direction. Yes, the displacement is 10 meters. So from where I've started to where I ended is 10 meters, but you also have to add that information that it's up or north or along the positive y-axis. See, it doesn't matter the path as long as I start and I end here. Now I'm like in 55 meters for my distance that I've traveled, but my displacement is still just 10 meters north or up because where I started and where I ended is path independent. Okay, so it doesn't matter how far I travel. If I end up being 10 meters north of where I started, that is always a displacement of 10 meters north, no matter the path. Okay, hopefully this is making sense. We'll look at some more examples. Let's do one more. Let me pause it here while I get this one set up. All right, so here's our last one. Let's say we go out our front door. We're going to go northeast 26 meters, and then we're going to go northwest 17 meters, and then I'm going to go southeast 38.1 meters. So, first one, what is my total distance traveled? This would be like the odometer that's read on your car. All right, so to be able to get that, we're going to just add all of those different paths that we went. So we're going to say, and I'm using my handy dandy calculator. So it's 26 meters. I went northeast, and then I'm going to add 17 meters to the northwest. That's 43 meters. And then I went southeast 38.1 meters plus 38.1. And that's going to give me 81.1 meters that I've walked total. So that is my path. My distance is my path. But now, step two, what is my displacement? Okay, remember, displacement is where you started versus where you ended. It does not matter about the path. Okay, so I'm going to click sum up here to see. So remember, there's two pieces of information you have to tell for displacement. It is a vector. Vectors tell you two pieces of information. So if I click sum, or you could just look on the graph here, it does not matter how much I went north or south because I've ended up here. That means I've traveled a displacement of 45 meters. But wait, there's more east that way east. So that means the vector, the displacement, has to tell you the distance and the direction that you went. It does not matter what the path is, just where you ended up. So I ended up 45 meters to the right or east of where I started. Now that's it. That's distance versus displacement. So tomorrow we're going to do some practice problems at the beginning of our video, and then we will go on and how this relates into speed and velocity. Speed is not a vector, velocity is. Boys and girls, hope that has helped. Welcome back. Okay, yeah, woohoo! Go physics.